All right, welcome to Easy Math with Nick. Today we are on video number 17, lucky 17. And today we are going to be doing, as promised, an AP Statistics free response question, specifically number 3 from the 2023 exam. So let's get right into it. This is going to be a quicker video, at least that's my goal with it, so not too much yapping for me. Bath fizzies are mineral tablets that dissolve and create bubbles when added to bath water. Ooh. In order to increase sales, the Fizzy Bath Company has produced a new line of bath fizzies that have a cash prize in every bath fizzy. Ooh, every one you get money. Let the random variable, x, represent the dollar amount of the cash prize in the bath fizzy. Probability distribution of x is shown in the table, so I give you a nice table. Based on the probability distribution of x, answer the following, show your work. So first they ask you to calculate the proportion of bath fizzy that contain $1. Okay, so we know that every bath fizzy has to have a cash prize, right? So there's no potential to not get a cash prize, right? So you can't get $0. That's not an option. So this table, the first row there, the cash prize X, that shows every cash prize possible, of which there are 6. So this shows the total options that you can get. You can't get over $100 either. Because they don't show that there. So if we want to find the proportion of bath fizzies that contain $1, we're going to do 1 minus 0.2 plus 0.05, 0.05. So essentially, what we're doing here is we're doing find the probability that we don't get get more than $1, essentially. We don't get any of the other cash prizes, which, because they're mutually exclusive, they're complementary events, sorry. You calculate by doing 1 minus the probability of the other event happening. So that's why this works. So if we do the calculation quickly, I don't have a calculator, I should. Let me, it's right across the table, let me grab it. Don't neglect your calculator. Use it always. Even in statistics, especially in statistics. So it's going to be 1 minus 0.32. It's not minus, that's an equal sign. Which we get a proportion to be, a proportion doesn't need to be a fraction, by the way, 0.68. So we have a 68% chance of just getting $1, which probably means you're losing money when you buy these. So don't buy these to get money. Calculate the proportion of bath fizzies that contain at least $10. So if we're looking at least, that means $10 and over. So we're going to be looking at these 3. So, I'm sorry, those 4. I cannot count. Those going to be 0.05. Proportion could be a decimal. So, oh, I'm sorry. Proportion of bath fizzies that contain at least. Oh, I'm sorry. Proportion. No, that's right. A proportion could be a decimal. I'm sorry. It could either be a decimal or a percent, not decimal and a fraction. I don't know why I said fraction. Because I'm thinking, no, that's fine. It could be a decimal. It still could be a decimal. That doesn't change anything. But for some reason, when I thought proportion, I thought fraction. But I don't think you would represent that as a fraction anyway. Plus 0.01. You could also say 68% of bath fizzies will contain $1. But I don't think that puts your odds any better. So you get 12% for part I. I'm going to write it as percent from that one, but so that's the proportion of bath fizzies. 12% contain at least $10. So there you go. Even though they give you probability, you can convert that just directly to a proportion by stating that 12% of bath fizzies will have that amount, because we're looking at an interpretation of probability where after we're dealing with a lot of bath fizzies, like as we have a large amount of them, the probabilities will tend to what we have in the table there. So then that could accurately represent the proportions that we get in our answers. So that's sort of the rationale behind why we can convert from probability to proportion. Because when we have a lot of these fizzies, right, which I'm assuming they're creating a lot of these, right, new line of bath fizzies are probably producing, millions of these. These probabilities here will went nicely to the proportion that we actually see in real life. So that's why that works. Okay, but they're not interchangeable. I thought for a second maybe they were, maybe that was a mistake I made mentally. But let's continue. This was supposed to be a short video. Based on the probability distribution of X, calculate the probability that randomly selected Bass fizzy contains 100, given that it contains at least 10. Ooh, there you go. That changes the question a lot because now it switches it from standard probability conditional to conditional probability. When you see something given us a different condition, we're dealing with conditional probability. That's in the name, right? And that states that if with probability of F given E, where F and E are two like different events, equals probability. This is on your equation sheet, by the way. F and E, that's all that means. Over probability, oops, it's supposed to be a P, not an F. Probability that E occurs. And so we're solving for this. So probability F is, let's say F is the event that $100, we get 100. And the E is at least 10. $10 or plus. So that's what that means. E is the event we get at least $10. F is the event that we get exactly 100. We get the $100. We win. Send it on Twitter. Show all your friends. Wow, I just got $100 from this Bass Fizzy. You should all buy it. Don't do that. Whatever. I'm losing it. But now we can just solve for what we're looking for. For part I here, we already found the probability. We essentially found the probability of Bath fizzies that contain at least 10%, which is 0.12, right? So we have the bottom here of this equation. We have the bottom part of, we have the denominator here, 0.12. But the top is the probability of F and E. What does that mean? That's the probability of getting, that's the, what we call the intersection between these two events. So that's going to be what the overlap. That's the overlap between those two events, which is what? What is the overlap? It's the overlap event is going to be getting $100 because 100 is greater than 10, right? So if we look at like a Venn diagram, this is F. F is getting $100, right? This is E. F and E, I mean, obviously F includes all of E. That's not a good example because it's not a Venn diagram because F is just part of E. So it's E and F. What is shared by E and F? The entirety of F, because F is part of E. That's not really a Venn diagram. I thought it would be, but no, it's not. It's just part of E because E accounts for $100 because it's 10 and over. And 100 is the maximum amount, which is over 10, right? So probability of F intersect E is really just a probability of F. So what does that mean? Well, that means we substitute the probability at F, which is 0.01. So what this is going to give us is, given that we know we got at least $10, this is going to give us the probability that we got $100. So we do that. We plug that into our calculator. We get that ungodly number. We convert that to a fraction for you. It should be 112. Yeah, which is 112. I'm going to leave it as that. That's our probability for part B. Great. Now, part C, based on probability distribution of X, calculate and interpret the expected value of the distribution in cash prize. Okay. When we're looking for the expected value, right, essentially what they're asking us is, when you open one of these Bath Fizzies, how much money should you expect to get? If you open just one on random, how much money should you expect to get? That doesn't necessarily mean that the expected value it could actually be a value that you can't actually get, right? When we get the answer for this question, it could be a value that that isn't even possible. It could be between $10 and $20. It could be $15, let's say. The expected value is 15. Can you actually get $15? No. But if you open up a lot of these Bath Fizzies, maybe when you take the total amount you gained from all those Bath Fizzies and divide by the number of Bath Fizzies you open, you'll get $15, even though you can't actually get $15 from one Bath Fizzy. So when we look at the expected value of the distribution, that doesn't mean it's a value that you can actually a value that actually you can get. It's hard to explain. So it's not, if it turns out to be $1, $5, $10, $20, $50, or $100. If it turns out to be 1, 5, 10, 20, 50, or 100, that's great. But I'm pretty much 100% sure it won't. So I'm pretty certain it won't. So let's solve for the question. We're going to use what we found in part A, part I, where proportion of bath fees that can contain $1, 0.68. So we're going to do 0.68 times $1 plus 0.2 times $5. 20% chance of getting $5. That's not too bad, actually. And 5% chance. Okay, goes down by quite a bit. For $10, right? Was that $10? Yes, that's 10. And same thing for 20. Same percent for 20, which is a little odd, but I won't judge. Plus 1% for 50 and 100. Okay. Same chance of getting 50 as 100. It doesn't feel right. Whatever. I don't know why they have it like that, but I'm not going to question the college board here. So this will get us our expected value, because when we add up all these decimals here, we're going to get 1. So that sort of explains the logic we're going to get here when we multiply all that out and add it up. Going to get what we should expect to see was like the average, was the expected value of the distribution, right? There's no other better way to explain that, I'm afraid. There might be, but beyond my and if you got a value that seems unreasonably large, you can redo your calculations. So make sure to use common sense when you do this question. 4.68. So that does make sense. So, and we say that's equal to the expected value of that X distribution, the cash price. Yeah, there you go. Cash price distribution, which is what we used up there. The dollar value, the cash price, right? Distribution of the cash price, I assume in dollars, right? What else would it be in? Okay, part D is where it gets interesting. It switches it up a little bit. The Fizzy Bass Company would like to sell the fizzies in France. Whoa. Wow. Where the currency is euros. Okay, that changes things. Suppose the conversion rate for dollars to euros of $1 equals 0.89 euros. Oh, that's interesting. That still stays true today. Well, not the exact conversion rate, but what stays true about that is I'm pretty sure even at this exact moment, euros are worth more than dollars. So back in 2023, that was still the case. So maybe that's been the case for a lot longer, and I don't know that, but I remember reading somewhere euros are worth like slightly more than dollars. So that's why that conversion rate makes sense. Forget it. That's not necessarily something you need to know, but they give it to you. Forget, I'm going off on a tangent, right? Using your expected value for part C, calculate the expected value in euros, okay, of the distribution of cash price and bath fizzy. Okay. This question is very simple. This is a linear transformation question. And what the hell do I mean, excuse my language, by linear transformation? You might have heard that word in your stats class. I'm like, what? What is that? Well, that essentially means is if we have like if we have a scenario where some distribution y equals m, or constant, times a distribution of another thing, say x distribution, when we find the mean of both of these distributions, let's say e of y equals a of m times x. When we find it, I'm sorry. Well, okay, I could go with that, but what we could essentially do is we could pull the m outside of, when we take the mean, we're just essentially what we're doing is we're just multiplying every x value by m, which means we could just pull out that m. When you calculate the mean, it's just you're adding up every value and dividing by the total amount of values. When you multiply every value by a constant, you could just pull out that constant. So when you're finding the mean, so when we do e of y, mean of expected value, that's what that means. As I said before, it's just that constant multiplied by E of x. The reason I use m is just to show that this is just very similar to when we look at a linear function, right? It's essentially just a function. But that's just why I use that. It's familiar. Not to confuse you. And this is not, we're not like looking at a slope or anything here, but that's just why I use that. Because it's familiar. And so when we look at, because that m here, when we look at what that m is going to be here, it's a conversion factor. So in this specific scenario, so we have, was our e of x, our e is 4.68. But we're now multiplying each dollar value by 0.89, right? Because we want to get from dollars to euros. Say we have like $400, 400 American dollars. If we're doing unit conversion, we would have to multiply by 0.89 euros, which is like something like, what's the euro symbol? Oh, I used to know it. Just going to say euros. I used to know the euro symbol, but I forgot how to write it. It's annoying. $1. So the dollar units cancel. Well, so that's why we're multiplying by 0.89 euros, because we're canceling out. We're swapping units now. So now that we're multiplying every dollar value by 0.89, that is our conversion factor when we look at our equation here. So it's going to be 0.89. That is our m. So expected value of this new distribution, which we're going to call e of y, 0.89, times what we just found in part C, 4.68. So, and now we're in units of euros, which I'll indicate in my answer, even though I didn't do that for the last question. So we get 4.1652 euros. It doesn't need to be capitalized. Whatever. I can care less. There you go. And it should be dollars. There you go. So that's this entire question. This was a pretty interesting question. I liked it because it showed a practical example of conditional probability, which I like. I always like those types of questions, where it wasn't a scenario where they give you something, but that doesn't change the probability. That would be like when the events are completely mutually exclusive, right? Where giving a condition doesn't change anything. No, this question did. The condition did change it a lot, because it went from what? 1% to 1 in 12, which is from 1 in 100 to 1 in 12 chance, given that we know that it's at least $10, right? So that was very interesting. I like that the most. Part A, I, and II, the first two questions in Part A, weren't that interesting, unfortunately. But I guess you could say this is sort of showing that, like, probability of y equals 1 minus probability of y complement, right? Something like that, where like complementary events have to, the probability of them occurring has to add up to 1, or you know that, right? I mentioned that briefly in passing, but you don't even need to like officially use that notation unless they require it on the exam. As I mentioned before, I did not take AP statistics. I mean, I do have statistics knowledge, but I didn't actually take the specific advanced placement course. So I don't know if what I just did here follows what they're looking for, but I answered the questions, and I think my answers are right. So that is all for today. Thank you for watching. Next video will probably go back to physics, probably one more physics FRQ. And then after that point, I'll probably make a return to more lecture style content instead of questions. Or maybe I'll actually go lean in heavily to the question style content and do like some SAT math questions or something like that, like hard SAT math type questions, because I know one of my viewers suggested I do something like that. So because those could be very useful to some people. So I think that might be the route I take. But we'll see. Next video, planning going back to physics stuff. So that was it for today. If you have any questions, be sure to leave a comment, and see you in the next one. See you. Thank you for watching.